Welcome to this course Fundamentals of Compressible Flow. We are in a new module 7. Name of this module is Compressible Flow with Friction and Heat Transfer. So, in the first lecture of this module, we will deal with the compressible flow with heat additions, and to be very specific, entire analysis will be done in one dimensional medium. Like in other situations, we will also derive the fundamental equations for heat addition process, the flow property evaluations when heat is added to the compressible flow. Then we will now introduce a concept of thermal choking. Normally, choking is the word which is used when the flow is sonic. Now, in this case, the thermal choking will mean that the sonic flow is achieved through heat transfer process. Now, by introducing this thermal choking, we will see how the flow property parameter gets changed and how it becomes easy for us to define a property table known as flow property table for heat addition process. Now, based on our understanding, we will try to solve couple of problems based on this topic. Now, just to revisit that whatever compressible flow in one dimensional we have studied, it was mainly done with an analysis that we have a rectangular control volume and it is imaginary nature. So, it is a, we can say it is a kind of a constant area duct. There is some inflow that is with certain flow conditions and there is some exit outflow at certain flow conditions, and based on these inflow and outflow conditions, we derive the relations for a one dimensional medium. And in this and in all earlier cases, we never dealt with a heat transfer process in this one dimensional medium, or there was no work transfer also into this medium. So, one such instances where we have seen that how the properties change could happen between 1 and 2 by considering a normal shock. So, the entire flow field is very discontinuous across this particular thin region, or we call this as a thin shock layer of typically dimension of 10 to the power minus 7 meter. And across this shock layer, we say there are large gradients in the flow properties inside the shock structure that results in the change in the viscosity and thermal conductivity in the medium. So, in this way, in this thin region the flow happens to be also a process that increases the entropy. So, even though the entire flow field is isentropic, but within this region the flow is non-isentropic, and in fact, we have proved that entropy always increases across a normal shock. And wherever and when you derive these relations for entropy change, we the pressure and temperature jumps are such that it does not explicitly we do not explicitly talk about the increase in entropy, because the already enhanced properties of pressure and temperature has ensured that entropy will increase. But in this process also we say that entire imaginary duct which consists this normal shock is adiabatic in nature. In fact, there is no heat addition into this process. Now, we will move to the in the similar logic we will now move to another situations where we will say that we have same one dimensional medium which is a rectangular control volume, and we can say it is an imaginary duct consisting of large streamlines. But what is the basic difference between earlier system and this, that we are going to add some heat into this duct, imaginary duct. So, this is one way that flow property can change. The other properties, properties in which the other mechanism in which the flow properties can be altered is through friction. So, in general there are three possible methods in a one dimensional medium for a compressible flow in a constant area duct. So, those methods are a normal shock, which you have already covered, and that is in adiabatic situation, and next method is heat addition or rejections. Obviously, it is a non adiabatic case since heat is being added or rejected. So, this is the main theme of this lecture, and last one is the friction through addition and subtraction of length, which is also a non isentropic case because it involves frictions. So, we will see these particular aspects in the subsequent class. So, our main focus is that what will happen to a compressible flow when heat is added. So, the possible situation could be, your condition 1 could be subsonic or supersonic. Now, if we say that it is a subsonic flow, what will happen to downstream situations? That is, if condition 1 is subsonic. And again, if the condition 1 is supersonic, what will happen to the downstream situation if the condition 1 is supersonic? So, these are the few questions we are going to answer from our analysis. So, to do all this analysis, we have to revisit the fundamental equations again. Now, just to say that what is the mechanism of heat addition process in a one dimensional flow, we can say that in this particular duct we are looking at the flow phenomena through an heat addition process. Of course, there is no normal shock which is sitting in the flow, where in which we could have said that there are drastic change in properties. But what change the flow properties is the heat transfer. So, as I mentioned that if for inflow can be subsonic, we will try to find out answer that if I add heat or subtract it, what will happen to the downstream condition 2, or in vice versa, if the inflow condition is supersonic, what will happen if I add or subtract heat in the to the downstream conditions. So, these are the few questions which we are going to answer in this analysis. So, the very basic philosophy of bottom line is the fact that heat transfer is the driving factor. But since there is a addition of heat, so we can say the entropy is going to increase or decrease. If heat is added, entropy is going to increase. If heat is taken out from the flow, entropy is going to decrease. So, increase in heat, addition of heat will increase the entropy, or rejection of heat will decrease the entropy. So, this heat transfer addition into a one dimensional flow has many applications. One such application is that the next generation type ground facilities like laser heated wind tunnels. So, people are thinking of, researchers are thinking of to develop a laser heated wind tunnel in which the property conditions of the flow can be altered by through the heat addition process using a laser beam. So, this when heat is added through this laser beam radiations, the gases or the gases that gets heated up and they change their flow properties. And in the this is one type of application where the aerodynamic facilities, next generation aerodynamic facilities are built with. The next type of heat addition mechanism happens during a fuel air combustion process. Normally high speed aerospace vehicles use a different kind of engines known as ramjet or scramjet engines. They are in which we consider the fuel air combustion. So, in such process the heat is added into the medium through the because the when you combust a fuel and air, the enormous amount of heat is generated into the medium. So, thereby it alters the flow properties of the mixtures. So, these are the some of the applications in which the heat addition has shown its significance for a compressible flow. Now, let us discuss about the heat addition process in detail. So, the first thing that we are going to discuss is the heat addition process, which is in a one dimensional medium, and we consider a rectangular control volume with certain inflow conditions, which is denoted by region 1. The output the outgoing flow conditions are denoted by the region 2, but what changes the properties is the heat transfer, which is certain amount of heat is added into this medium. So, we say that the flow occurs in a constant area duct. The flow is considered to be steady for a calorically perfect gas. There is no work interaction, body forces and frictional effects are negligible. So, these are the assumptions based on which the one dimensional flow equations are governed. So, the entire idea for this analysis is that the conditions 1, they are commonly known as known conditions, and the region 2, these are the unknown conditions. So, our main task, like in earlier cases we did, is that to express all the downstream parameters, like all unknown parameters, as a function of upstream Mach number and the upstream parameter and the flow Mach number. So, all output conditions are region for the region 2 we have to express as a function of region 1. So, the property parameters are defined with respect to known parameters for the region 1. So, the next aspect we are going to study about this is that with this control volume of one dimensional medium, we are going to write the fundamental equations. So, those equations are conservation of mass, and so this first equation which is written here is the rho 1 u 1 is equal to rho 2 u 2. So, it is a mass conservation. Last the second equation which is used is P 1 plus rho 1 u 1 square is equal to P 2 plus rho 2 u 2 square. This is the momentum equation. and last equation, that is H1 plus U1 square by 2 plus Q is equal to H2 plus U2 square by 2. So, this is the equation that is going to change in our earlier situations, because Q is introduced as a heat which is being added into the flow. Now, from these energy equations we can express, so we can write the H, the enthalpy for a calorically perfect gas as Cp times T. So, for condition 1 and 2, when I from the energy equation, if I take out Q, then I can write Q is equal to Cp T2 plus U2 square by 2 whole bracket minus Cp T1 plus U1 square by 2 whole bracket. So, this we know that the total Cp T plus U square by 2. So, T naught we can write or you can write Cp T naught would be equal to Cp T plus U square by 2. So, so the first equation now becomes, so the energy equation, from this energy equation we can derive this particular value of Q as Cp times bracket T naught 2 minus T naught 1. So, in other words, the heat addition is expressed as a function of total temperature. So, this is the first step, and next step what we are going to look at the flow property calculations, and here we will deal with the static property ratio. By static property ratio I mean P2 by P1, T2 by T1 and rho 2 by rho 1. So, to start with the static property ratio, we have to consider the momentum equations. So, this particular equation is considered from momentum equation. So, from this momentum equation we write this P2 minus P1 is equal to rho 1 U1 square minus rho 2 U2 square. Then what I use this relation Mach number as U by A. So, this will implies U is equal to Mach number times A. So, for condition 1 and 2, if when I put U as m times A, so I can write rho 1 A1 square m1 square minus rho 2 A2 square m2 square. So, again the A we know that is nothing but equal to gamma A square is equal to gamma p by rho. When you put this relation here, we are now able to express A square as a function of pressures. Now the main equations which was we are here, we now write P2 minus P1 is equal to gamma P1 m1 square minus gamma P2 m2 square. So, this equation is simplified to this in this part. Okay. So, now we are able to find out pressure ratios as a function of Mach number m1 and m2. The second property which we are going to evaluate is temperature ratio. To know the temperature ratio, we will have to recall that the equation of state. So, equation of state says that P is equal to rho r T. So, for condition 1 and 2, I can write P1 is equal to rho 1 r T1, P2 is equal to rho 2 r T2. So, this will give a relation that T2 by T1 is equal to P2 by P1 in whole bracket into rho 1 by rho 2. So, you can either you can put in the bracket. So, now in this equation we already know the pressure ratio P2 by P1 from the above. We now require rho 1 by rho 2. So, this rho 1 by rho 2 we will get from continuity equation, like rho 1 U1 is equal to rho 2 U2. So, this will tell you that rho 1 by rho 2 is equal to U2 by U1. Now, again U2 is equal to Mach number times A, we can write this, and also the here we will now write A2 by A1 as also a function of T2 by T1. So, we can write that A square is equal to square root A square is equal to gamma R T. So, for condition 1 and 2, this is expressed in the form of T2 by T1 to the power half. So, final expression now stands as T2 by T1 is equal to P2 by P1 into M2 by M1 into whole bracket T2 by T1 to the power half. So, we can bring this particular term here. We also know the pressure ratios from these equations. So, ultimately we get a net results in the temperature ratio by this form. So, once we know the temperature ratio, we can also find the density ratio. So, density ratio is rho 2 by rho 1, again using equation of state we can write P 2 by P 1 into T 1 by T 2. So, prior to this we all know the expressions of these values. So, after simplification we can arrive at this. So, in other words, what we have done here, that for condition 1 and 2, pressure, temperature and density, pressure, temperature and density at the upstream and downstream conditions, they are expressed as M1 and M2. So, obviously, when you know the pressure, temperature and densities, pressure and temperature ratios, we can also evaluate what is happening to the change in the entropy. Now, effectively this particular expression does not explicitly focus about the heat addition process, but this heat addition Q has already changed the properties P 2 by properties ratio P 2 by P 1 and T 2 by T 1, and these ratios are mentioned here. And since it is a heat addition process, so entropy will increase. This is how we get to know that how we are going to evaluate the static flow properties during this process. Now, we will move on to the flow property calculations with respect for stagnation conditions. For stagnation conditions, we are now left with two parameters, one is stagnation pressure, other is the stagnation temperature. So, the stagnation properties, so what I can say is for the condition 1, which is we can say U1 or Mach number M1, for the pressure P1 and Mach number M1 we can define P01, and for temperature T1 and Mach number 1 we can also define T01. For M1 and rho 1 we can also define rho 01. So, and similarly for U2 and M2, this will talk about P02, T02 and rho 02. Now, from isentropic relation we all know actually here we are mostly important parameter is P naught 2 and T naught 2. So, we can write the P naught by P is equal to 1 plus gamma minus 1 by 2 m square whole bracket gamma by gamma minus 1 T naught by T is equal to 1 plus gamma minus 1 by 2 m square, and rho naught by rho is 1 plus gamma by minus 1 by 2 m square whole bracket 1 by gamma minus 1. So, these are arbitrary properties we can now define as P naught 1 by P 1, T naught 1 by T 1 and rho naught 1 by rho 1. Similarly, we can write T naught by T 2, P naught 2 by P 2 and rho naught 2 by rho 2. So, here it is a function of m 2, this is a function of m 1, right. So, but we are now require the ratio between P naught 2 and P naught 1. So, we write this P naught 2 by P naught 1 as P naught 2 by P 2 into P 2, and in the denominator it is P naught 1 by P 1 into P 1. So, this P naught 2 by P 2 we get from this expressions where m is replaced with m 2 and P naught 1 by P 1 is replaced by same expression where m is replaced by m 1. Also, we already in the static property relations we already know what is the value ratio of P 2 by P 1. So, after putting this we are now in a position to simplify a relation which is P naught 2 by P naught 1. So, in the similar manner one can evaluate the stagnation property ratio T naught 2 by T 1 and they are expressed as both function of m 1 and m 2. So, this is how we are going to evaluate the stagnation properties. Of course, once you know P naught 2 and T naught 2, one can also evaluate also rho naught 2, where rho naught 2 can also be written as P naught 2 by R T naught 2. So, likewise all properties of downstream conditions are expressed as function of upstream parameters. Okay. So, with these equations we are now summarize that how we are going to evaluate the downstream flow properties for a heat addition process in a one dimensional compressible medium. But if you look at actually these equations, what we have seen is that let us take a particular equation, let us say T naught 2 by T naught 1. So, to evaluate T naught 2 by T naught 1, we require, so if we want to find out T naught 2, we have to know T naught 1, m 1 and m 2, then only we will be able to find the T naught 2. But in general the region 1 is generally known condition and region 2 is unknown condition. So, effectively we do not know, effectively we have two unknown parameters in the region 2, that is T naught 2 and m 2. So, even this also is true for all other relations where we need to require at least one parameter in the downstream, either Mach number or any of the static properties. So, here, but to do that we do not have any other choice, rather we only know that some heat is getting added into the medium. So, to do that, what we see is that we can express this Q as C p times T naught 2 minus T naught 1. So, from this equation we can evaluate T naught 2 is equal to T naught 1 plus Q by C p. So, in this equation what we know is T naught 1, Q and C p. So, we can this is a known quantity. So, with this known upstream parameter, we only know one downstream parameter T naught 2 as T naught 1 plus Q dot Q by C p, it will be C p, it will not be Q dot, it will be only Q, right. So, the process would be that. So, what we now next step is that you calculate T naught 2 by T naught 1. When you calculate T naught 2 by T naught 1, it will give, for this ratio we are now in a position that to use these equations of T naught 2 by T 1, where this is a known parameter, this ratio is a known parameter, we have on known parameter m 1. So, iteratively we have to do a trial and error approach to find T 2, find m 2. So, this is how the iterated approach is involved to calculate Mach number m 2. Now, we are in a position that we know m 1, we also know m 2. So, then all other parameters can be calculated from this process. So, but this and entire calculations involves the trial and error process only for the calculation of Mach number. To avoid such calculations, what we are now going to propose a concept with respect to a reference conditions. So, what does this mean? That had the flow been sonic at the exit, what would have been its condition? Like for a given arbitrary condition of 1, if the flow is going to be sonic, if we say condition 2 happens to be sonic, sonic means I can say at this case we are saying Mach number as 1, sorry. If we add continuously heat into this duct such that the condition 2 for which Mach number is sonic, then we can define a reference condition T star as P star, T star, rho star, P naught star and T naught star. In fact, this is also true that one can bring this condition to star. This is also possible that we can bring this condition to star conditions. When I say star condition, that point I will say its Mach number will be 1. Here I say Mach number will be 1, but how the star condition is reached? Through heat transfer. So, it means that the a sonic flow reference condition can be achieved hypothetically by choking the flow through heat addition or rejection. Such a method is known as thermal choking. So, here we introduce the word thermal choking because the choking conditions or sonic condition is achieved through heat transfer. In all other previous instances, we also defined the choking conditions, but that was with reference to the mass flow rate. So, that is the basic difference, that how a thermal choking is different from the mass flow rate choking. Now, to simplify this analysis, let me cite this example by using a pictorial representation. For instance, we have a duct, one dimensional duct, where the condition 1 is defined. We have also for a given condition, we have some downstream condition 2 like M2, P2 and rho 2. So, the change in the flow properties is achieved through a heat transfer is Q. Now, what we imagine? So, this is a real condition, a real situation. So, this is a real situation, and in a hypothetical situation, what we assume that if I can add if I want to go from the condition 1 to a sonic state through heat transfer. So, I have to add a magnitude of heat, that is Q 1 star, such that your M will be such that at the downstream Mach number will be unity. So, under those circumstances, I can define this pressure condition in the downstream as P star, T star, rho star, P naught star, T naught star and rho naught star. So, with the same logic, if I will go from condition 2 to get this star condition, so that the flow is sonic at the downstream, then I have to add Q 2 star amount of heat. Thus, since both the states are a hypothetical state, but the very basic fact that by assuming these hypothetical states, I am able to calculate the amount that I am going to add, since the reference conditions are same for the both the states. So, this will give me a equation that from this pictorial representation I can say the amount of heat that I am going to add in a real situation is nothing but the hypothetical heat transfer Q 1 star for the state 1 and state 2. And in fact, we will now show that how this particular concept will help us in simplifying our flow calculation properties. So, if I do that, all governing equations for the static properties ratios or stagnation properties ratio, like if you say that for the star condition, if you put Mach number as 1, those equations can be simplified in this fashion. So, and in fact, what we see in this equation that P, T, rho are any arbitrary properties for any real situation, and star parameters, they are the corresponding imaginary states when the flow is brought to sonic state through heat addition. So, in such cases the equations get simplified and what we see is they are only function of Mach number. So, this gives an indication that we can form a table just by changing the Mach number and find the reference state, find these ratios, so that it will help us in simplifying our calculations. So, that table is known as one dimensional table with heat additions. So, this table is presented here. So, it is taken from the extract of the book John D. Anderson, that is Modern Compressible Flow with Historical Perspective, McGraw-Hill. What has been shown is here, I have just taken some extract from this. So, there are about 6 columns. So, the first column talks about the Mach number, that means if you know the Mach number, then we can find out these property ratios P by P star, T by T star, rho by rho star, P naught by P naught star, T naught by T naught star. So, this table can be prepared. In fact, if we are not really supposed to know the or remember those equations, big equations, rather just by referring the table we can find out, just by knowing one value in this table we can find out the complete information in that row. For instance, if I know P naught by P naught star as maybe 1, then I can say that all the numbers in that row are known. So, this gives a very easier method to evaluate the flow properties in a heat transfer situation in a compressible flow. Now, with this logic we will now try to solve some of the some simple problems which will talk about how one has to refer a gas table for a given flow situations. So, the question that is given is that a supersonic stream of air enters in a constant area duct at a flow Mach number of 3 at a pressure 0.9 bar and 20 degree centigrade. So, the question that is asked is how much heat is required to choke the flow. Calculate the flow properties in the downstream. In the downstream means what are they? What properties you need to calculate? The Mach number, static pressure, static temperature, density, stagnation pressure and stagnation temperature. So, what the problem that is given to us is that we have constant area duct, so we draw these situations, whatever the flow is entering from region 1, and here the conditions that are given as m is equal to 3 or m 1 is equal to 3, P 1 is equal to 0.9 bar, T 1 is equal to 20 degree centigrade or 293 Kelvin. What is required? At the condition 2, we say that the condition 2 is achieved by choking. So, choking the condition means here we say M 2 is nothing but 1. So, for this condition 1 we have to find out, to get this condition 1, how much Q we are going to add. So, we also have to require P 2, T 2, rho 2 and P naught 2, T naught 2. So, these are the important parameter which needs to be found out. But before you start this, we can recall that this Q is nothing but Cp times T naught 2 minus T naught 1. Now, since this is not known, we have to find out, and T naught 1 is known to us. So, how do you first find out T naught 1? So, T naught 1 is 1 plus gamma minus 1 by 2 m 1 square into T naught 2 1 by T 1 is this. So, you know m 1 as 3, then this will give you T and T 1 as 293 Kelvin. So, this will tell you T naught 1 would be 820.4 Kelvin. Just put m 1 is 3. So, I can write T naught 1 as 820.4 Kelvin. Similarly, we can write P naught 1 by P 1 as 1 plus gamma minus 1 by 2 m 1 square to the power gamma by gamma minus 1 whole bracket. So, this will say P naught 1 would be 33 bar. So, I say P naught 1 is 33 bar. So, what I am now going to see that if for a upstream Mach number of 3, by adding heat, if I want to choke the flow, then I should refer the Mach number m as 3 in this particular column of Mach number. So, here we can see the 3 achieves in the last row, 3 we can get at this number as Mach number of 3. So, for that I can say P 1 by P star as 0.1765. I can note down all the values in this row, T 1 by T star, because I have found out the it is for this condition 1. So, P 1 is replaced as P 1, T 1 is replaced as T is replaced as T 1. This is 0.2803, rho 1 by rho star is 0.6296, P naught 1 by P naught star 3.424, T naught 1 by T naught star as 0.654. So, I can find out T naught star as T naught 1 by 0.654. This number would be T naught 1 is known. So, we can find out this value as 1254 Kelvin. So, we can say Q is equal to Cp, that is 1.005, T naught 2 1254 minus 820.4. So, this number will be about 436 kilojoule per kg, because Cp is 1.005 kilojoule per kg. So, thus we are able to find out how much heat is required. The next, once we know this, we all know all property parameters P 1, T 1, T naught 1 and P naught 1. So, from these ratios we can say P star as 5.1 bar, T star can be calculated from this expression, that is 10 4.3 Kelvin, then rho star is equal to 1.72 kg per meter cube. We also can know that P naught star as 9.63 bar. So, these numbers are very simple because we know this ratio, we know all the upstream parameters. So, the star conditions can be found out, but the most important segment is the value of Q. And here the important information that is required is T naught star to calculate Q. Okay. So, this is one problem. Okay. In the second problem, what has been given with the same upstream data of question 1, if heat added is 0.3 megajoule per kg. Like in we have shown that in this case your heat added to choke the flow is required is 436. Okay. Now, the question says here, now we do not want to add 436 kilojoule per kg, we are going to add only 300 kilojoule per kg or 0.3 megajoule per kg. So, in that case what is going to happen in the flow properties. So, here it is the conditions 2 is not a star condition, the conditions 2 is any real situation. So, we define this as P 2, T 2, rho 2, M 2, P naught 2, T naught 2. Condition 1 as P 1, T 1, rho 1, M 1 that is 3, P naught 1 and T naught 1. So, from the last and heat is added, Q is equal to 300 kilojoule per kg. From the last last question data, we can gather the information for M 1 is equal to 3. For M 1 is equal to 3, we say the data which are known to us P 1 0.9 bar, P naught 1 33 bar, T 1 is 293 Kelvin, T naught 1 happens to be 820.4 kilojoule per kg and rho 1 1.084 kg per meter cube, rho naught 1 would be 14.22 kg per meter cube. So, these information are with respect to Mach number 3 from isentropic relation. Now, referring to this table for this Mach number 3, when heat is added to the choke the flow, we can say from this row we can say P by P star or P 1 by P star is 0.1765, T 1 by T star is 0.2803, rho 1 by rho star 0.6296, then P naught 1 by P naught star 3.424, T naught 1 by T naught star 0.654, right. So, this is the data which we get, but what is actually added is 300 kilojoule per kg. So, now I can write Q is equal to Cp times T naught 2 minus T naught 1. So, this will give you T naught 2 is equal to T naught 1 plus Q by Cp, and that number I can find out 1118.9 Kelvin. Then I can find out what is T naught 2 by T naught star. So, this is nothing but T naught 2 by T naught 1 into T naught 1 by T naught star. So, I can write this is 1118.9, T naught 1 is 820.4. This ratio T naught 1 by T naught star is 0.654. So, this will give you a value 0.892. Now, I am in a position to refer this table for this ratio. If you look at this number, then we will find that there are two numbers which is close to it. One is 0.8935, other is 0.899. So, this will give you your M2 can be 0.68 or M2 can be 1.54. So, there are two values, one is subsonic, other is supersonic. So, what has been seen here that the subsonic solution will be a real one, will not be possible, whereas supersonic solution will be possible. Why I will conclude, I will come to this in the next class, because the supersonic flow without coming back to sonic flow, it cannot again go back to subsonic flow. That means, it is not possible to bring a supersonic flow to subsonic flow without reaching a stonic state. So, that is not possible. So, in this case we cannot reach the sonic state, we cannot reach the subsonic state directly. So, one solution that possible is your M2 should be 1.54. Now, when I say M2 is 1.54, then I can compute P2. So, I have to take all the data as this. So, I can say for M2 is equal to 1.54, we can say P2 by P star is 0.55545, T2 by T star 0.7319, rho 2 by rho star 0.759, P naught 2 by P naught star as 1.142 and T naught 2 by T naught star as 0.8992. Okay. So, once we know this, we can find P2 as P2 by P star into P star by P1 into P1. So, this number would be 2.83 bar. Similarly, we can say T2 as T2 by T star P2 T star by T2 into T2. So, we all know the property values here here and here. So, we can say T2 is 765 Kelvin. Likewise, I can compute P naught 2 as 11 bar, rho 2 as 1.306 kg per meter cube and rho naught 2 as 3.47 kg per meter cube. So, as we see that how this table makes the calculation simple. So, we do not have to explicitly use these equations. So, this is all about for this today's lecture. I hope I have made you understand for the content of this lecture. Thank you for your attention.